Hello girls, this is Mr. Wells recording to you from my secret Corona bunker. And this is the first of at least 2 videos that we'll be going through before we go on our spring break. So if you have not already gone onto Finalsite and gotten Study Guide 1, you need to do so now. Now the best way to do this, if you're watching this on your computer, is to have the study guide maybe on your phone or on a tablet of some kind. You could do that vice versa, have the study guide on the phone or tablet while you watch the video on your computer. But if you can print it, that might be best case scenario. So if you need to get that study guide, pause the video and do so now. So now I imagine that everybody is watching the video and has the study guide in front of them where you find a number of essential questions. So let's go through those essential questions first. What is a function? Well, we defined that a couple times in class over the last couple weeks. A function is a relation, meaning that it is pairing an input and output value. It is a relation where every input has exactly one output. Every input has exactly one output. If you recall when we drew the function machine needs to know exactly when you put something in, it needs to know exactly what's going to come out. The function machine can't have options for outputs. So if you put a value into a function, there is precisely one output. So we'll look at some things that are functions and not functions shortly. Your next essential question is, how are functions represented? So we've looked at that together in class. Might be good for you to take some notes as you're going along with us, as you see me writing here in lieu of having a whiteboard. So we have essentially 4 major ways to represent functions. One would be a table of values. The second would be a graph. A third would be, and maybe the least likely to be used, a mapping. And fourth, a function's rule, which we can also call an equation that represents the function. So we have 4 different ways to represent functions. And we're going to look at how we can look at one function and represent it in all 4 ways. So let's do that now. And let's start with the table of values. So remember, as I make this function, it needs to have every input mapping or going to exactly one output. So as I write my inputs in the X column, I'm only going to write each input exactly one time because it can't have 2 going to 3, 2 also going to 5. The function machine is not going to know what to do when you input a 2 into it if that were the case. So we're going to have all unique inputs. So let's say we have the fab 5, -2, -1, 0, 1, and 2. So all of these guys, it does now not matter what I put in the output column. I have all unique inputs, so I could put the same number over here for every value if I wanted to. We've seen that in class. That would represent a horizontal line. Or I can put a bunch of different ones. Now I have specialized functions, such as linear functions, that had to have particular properties. But this is just going to be any old random function you find lying around the house. So let's say that -2 goes to 0, -1 goes to 3, 0 goes to 4, 1 goes to, let's go to 8, and then let's have it come back down. 2 is going to go to 6. So this is my table of values. Compared to the same function when I graph it in the Cartesian coordinate plane with an x-axis and a y-axis, I'll be looking at each of these representing a unique ordered pair. So the first entry is -2, 0. So on the x-axis, I go -2, 0. Next, the second row gives me an ordered pair, -1, 3. So at -1, I move up to +3 on the y-axis. Now, I see I have an input value of 0, an output of 4, giving me the ordered pair 0, 4. So I have another ordered pair right there lying upon the y-axis. Now here, hopefully I've given myself enough room, maybe just barely, to get to the point 1, 8. Certainly I can get to 1 on the x-axis. We may have to cheat a little bit here and say 5, 6, 7, 8. Maybe not scaled perfectly, but I've got that going right there. Finally, the ordered pair, as I said, we would bring it back down on the y-axis. As you can see, this output is 6 compared to the output we previously had of 8. All of these were increasing outputs. Now suddenly I'm decreasing. That'll be important later. Ordered pair 2, 6. So 2, 1, 2, 3, 4, 5, 6. Right about there. So here's my graph of the same function. The table of values and the graph each representing the exact same relation. Now when I go to my mapping, this is where I had those ovally guys. And I had my x's and my y's. We're going to have different names for those guys soon. We are already calling them inputs and outputs. You also know them as independent variables and dependent variables. And we'll have another name, not until the next video, but all those input values, all 5 have to squeeze in here. So I have -2, -1, 0, 1, 2. Now recall what I told you in class. It doesn't matter what order these things are put in when they're in a mapping like this. So I could have written them in reverse order. I could have scrambled them up. It doesn't matter. But just for simplicity's sake, we're going to go ahead and just put them all right next to one another. And from the table of values, all these ordered pairs, the points that we plotted, we see that -2 goes to 0, -1 goes to 3, 0 goes to 4, 1 goes to 8, and 2 goes to 6. So this is what we call mapping. As I mentioned when we were writing up here, probably will be the least likely used. As you can see, a little boring. Anyway, representations of functions. You notice that I'm not writing an equation for this because there's only particular functions that we can write equations for. We have plenty of relations that are functions, but not all of them can be written using a rule, or at least a nice, pretty, and short rule. I could write a complicated rule for this, which would be annoying for everyone. I won't do that until we're ready to get through the rest of the unit. But anyway, let's move on to the next essential question. What is a linear function? Now, a linear function is one that we define to have a constant rate of change, which is the next essential question. What is a rate of change? Rate of change has to do with what is the relationship between going from one input value to the next output value. So you might recall as we made tables, let's just repeat the function we just had with a little more space. -2, 0, -1, 3, 0, 4, 1, 8, a little longer, 2, 6. To examine the rate of change, we're looking at that thing I called delta y over delta x. Delta being the small triangle, which is the math symbol for change. So I'm looking at what's happening as I go along each point. And traditionally, I would be numbering these in terms of their numerical value. So here, order is a bit important. We can get around it in a lot of ways, but here they're obviously in ascending order. To go from -2 to -1, I'm adding 1. And to go from 0 to 3, I'm adding 3. You remember doing this in class. Right away, I see that as I've added 1 here, I've added 3 here. I've added 1 again, but now I've only added 1 here. So I can see suddenly that the rate of change here is not constant. And you see that happening in the graph. If I were to connect these points, I have a rate of change of that right here. As x increases by 1, y increased by 3. But now suddenly as x increases another 1, y only increases by 1. So that's going to lead us to a conclusion that we've already talked about in class here that we'll go through again shortly. But again, x is going to go up by 1. Y now suddenly goes up by 4. Okay, so you can see I'm kind of connecting. It's like I have 3 separate lines. As I said, I could write a function rule to represent this graph, but it's not going to be as pretty as you would think, because right now I have 1, 2, three separate pieces, and now suddenly you see y's were getting bigger as x got bigger, but now as x gets bigger, y suddenly gets smaller. So whenever I'm looking at a function and I'm trying to determine whether or not it's linear, I want to know, does it have a constant rate of change? So I'm looking at each of these values. The change in y over the change in x, is that equal to the next change in y over the next change in x? 3 over 1 is obviously not equal to 1 over 1, so I know that I'm not looking at a linear function. But just to finish the thought, were I to have an equality here, I have to continue to have equality everywhere that I go. Now, obviously, none of these values are equal to one another. And even if I had this one equal to this one, which I don't, but if this one was equal to this one, it still would not be a linear function, because I would need to be able to check off all of these guys, and I can't check off any of them. Okay, so we'll have much more on how to identify a linear function here shortly, but linear functions have a constant rate of change, meaning that everywhere that you know about on the graph, on the table, in the relation, everywhere the rate of change, the delta y over delta x, is constant. When you make a graph, the graph forms a line. Now you might say, Mr. Wells, that looks like a line. Well, no, to me it looks like 4 separate lines. In math, to say that you have a straight line is redundant. All lines are straight. If you have anything other than a single straight line, you don't have a linear function. So we've got what a function is, how they're represented, what linear functions are, and what a rate of change is. So I think we're ready to start looking at exercises 1 through 5 on your study guide. So let's go ahead and pause the video here. This will be at least a 2-parter, and the second part you can go to in a moment.